you, Dr. Huang. I'm really glad to have this opportunity to present the current ongoing research work in our lab, which is orthogonal stall sensor for detection of cancer biomarker with accelerated banding kinetics. So a little bit of background. So when we talk about analyzing protein or quantifying, there are some of the well-known methods to do it. So we have immunosorbent assays such as ELISA and Western blot. We have like polymerase chain reaction to amplification of the DNA strand from the protein. Also, there are some optical-based methods such as surface plasmon resonance that utilizing the shift in the optical wavelengths and intensity to measuring the binding events. So for each, I didn't mention other methods such as mass spectrometry or radio labeled biomarkers because those are required extra process or expenses. But for some of the well-known protein analysis method, each has its advantages and drawbacks. And such as for Western blot and ELISA is well known. If you follow the protocol from available website, it usually take about 14 to 18 long hours to prepare your sample and do the entire assay. And also not saying like the overnight incubation of your pre-coded surface and also the assay, the data generation time. And also for PCR is known to have more expensive equipment required. Also, the technical training need to be given to the personnel, usually giving some of that expense to raise it higher. And for the surface platform resonance, it is currently like a novel protein detection method. However, it also has some drawbacks, such as if there's some non-specific binding to a sensitive surface, it's also causing enlarged background noises because of that non-specific binding. And also the equipment costs are usually high. So some of the challenges and goal to develop a point of care useful biosensor are mainly targeting addressing the following three aspects. The first is ideal to have a low detection limit by increasing the signal to noise ratio and also have a good specificity of your binding ligand and receptor. And also the idea to have a lower detection time so that if you're doing your biosensor with the point of care or in developing countries, you don't need to go to a hospital and then wait for your result for a long time. And also the specificity is also matter because that determines what is your true positive signal given and how reproducible are your assays. So the goal of the current of the presenting research are going to focus on these three aspects by addressing some of the low-cost fabrication methods, and also there's a label-free of your biomarker, and also you can do a real-time detection, and we can implementing a high-throughput parallel screening and by generating quantitative measurements. So these are the goal for this research. So the proposed research is called orthogonal dual-line surface acoustic wave sensor. So for surface acoustic wave sensor, it is known that on ST-Quartz wafer, we can generate two different modes of surface acoustic wave. The first one is called Rayleigh wave. So Rayleigh wave has been known of analogy to earthquake wave. So the energy is propagating in vertical distortion method, and whereas the surface of acoustic wave is propagating, it can be if it's meeting a liquid medium, is the surface acoustic energy can be damped to the liquid and causing fluid motion and also heat generation. And the other mode of surface acoustic wave is called shear horizontal wave. So shear wave is propagating parallel to your substrate. So it is known to be able to measure the mass loadings, such as saying like physical vapor deposition. By increasing the thickness of the metal deposition, we can have a signal response by comparing the input and output signals phase differences, or the change in the resonance if we're using an oscillator. So our goal is to combine the two modes of acoustic wave by using the shear horizontal surface acoustic wave to measure the real-time binding event between antigen and antibody. While for the analyte is the sample, we are only needing to put a small volume of sample, and that sample is going to be disturbed by the Rayleigh wave microfluidic mixing, so that the non-steady state movement of the sample is likely to increase the chances of the ligand and receptor conjugation. So by that is hopefully to have a real-time binding curve, and also to study the binding affinity such as association dissociation rate, while the equilibrium time will be pushed forward. So the shorter time are needed to reach the equilibrium. So what I said, like this is a low-cost method because we can do a single-step lithography to directly put in configuration for Rayleigh wave and shear horizontal wave. On the upper right is a fabricated device for the sensor. So at the middle, we have the reflector that helps to generate a more even Rayleigh wave mixing to the fluid. And on the parallel direction, we have the shear horizontal wave, and one is going to be coded with such as capture antibody, and the other one is going to be served as a noise canceling element from the ambient air, the air turbulence from the ambient environment, or the heat generation from the Rayleigh wave fluid mixing. And one thing notice is how this will be connected to the VNA as well as the RF generator. So the generator is going to matching the resonance of the Rayleigh wave, which is determined by the different acoustic velocity on different direction on this ST-cut core substrate. As I mentioned before, the Rayleigh wave can not only causing mixing, and it can also cause heat generation. So one of the things is that we don't want the heat generation. For example, we're doing protein analysis. We have known like the threshold of protein denaturing temperature is about 41 or 42 degrees Celsius. So we have known the temperature increasement from the Rayleigh wave mixing are in proportional to the RF power from the Rayleigh wave. So which means more Rayleigh wave power, there more temperature rises. So here we study the effect of the droplet volume of your sample and how your RF power is going to affect the temperature increase. And here we basically found like there's from 5 to 20 microliter size, which is our analyte needed for biosensing. There's not really much of the change in the phase shift from the shear horizontal wave, and there's not much the temperature differences between these different volumes. However, another thing is the RF power directly determined is proportional to the increase in temperature. And also the temperature increase will also cause a phase change in the shear horizontal surface acoustic wave signal that could be caused some artifacts when we are doing real-time binding event measurement. So our preliminary study has been done by studying the conjugation between carcinoembryonic antigen, and by first we pre-coded a protein A to have the antibody aligned vertically, so like more FAB specific region will be exposed to the epitome on the antigen. And then we are studying a different concentration of our carcinoembryonic antigen protein analyte. And then we measuring the phase response from this binding event to study the time-dependent binding curve by using the 3 different concentrations. And we clearly see that the first thing is at higher concentration and with the Rayleigh wave mixing, there is a steeper response curve from the Rayleigh wave mixing and causing the increased response from the binding affinity measurement from the shear horizontal wave response. So the conclusion is we have implemented the orthogonal stall sensor to study the binding event, and at the same time we use the Rayleigh wave to create a non-steady state liquid to generate some velocity inside of the liquid droplet to increase the time, to decrease the time to equilibrium. And by salt mixing, we find out the faster incubation time has been reached, and also the temperature increase can be controlled by implementing a smaller amount of Rayleigh wave RF power. And our future study are going to be implementing this sensor to do real-time binding affinity event to be able to calculate the association and dissociation rate, and also be able to quantify others like cancer biomarker by introducing enhanced mass loading, such as conjugation of gold nanoparticle to the detection proteins. And that concludes my presentation today. Thank you for your attention. I'm here open to answer the questions.